always use this schematics, which we like it a lot. Okay, so we have the standard basis and the other basis, where the standard basis it has an x0. Then, if we are given an x0, which is the initial condition in this basis, we should define immediately a u0. Okay, and this u0 here we have a mixed matrix A. Here we have a mixed matrix D, which is the diagonal matrix. And then if we have here xt, we should have here also ut. Okay? And then if we have a relationship which states that the derivative of a vector is equal to a times x0, here we have that the derivative of this vector is equal to d times u0. So now let's try to write both of these expressions. So here, and this is defined as dy1 with respect to time. So this we denote the derivative. It is, let me use a dot here. This is y1. This is derivative of y2. This is equal to 3, 2, and 2, 6. Multiplied by y1, y2. Okay, so this is the first expression. Then let's see. We have here apparently y1, y2. In this new basis, let's call this one uv. Okay, we like that this uv is just a pair of numbers. And let's see. First of all, we have the matrix A. Okay, this is A. What should we do immediately? We should try to determine what are the eigenvalues and the eigenvectors. Now, for any one of you who wants to do this fast, I mean, you can try the following. You can try this one on Octave Online, where you say that A is equal to 3, 2, 6. So this is just as a reference. And then you can write, to find the eigenvalues and eigenvectors, you can write the following. Vd is equal to eigen of A. Or you can also write the following, you can say P is equal to poly A, which finds the polynomial, characteristic polynomial of A, and then the eigenvalues will be simply the roots of P. Okay? So here we have some comments which you can type them fast on any MATLAB programming language or Octave. Now let's see. Matrix A is here. What is the determinant of matrix A? The determinant of matrix A is equal to, this is 3, 6. This is 14. 14. That's correct. This is 14. And then let's try to identify the eigenvalues. The eigenvalues
7
and 2.
What are those?
7 and 2.
7 and 2, that's good. So it looks like if there are 7 and 2, but we know what the procedure is. The procedure should be as follows: 3 minus lambda, 2, 2, 6 minus lambda, and then from here we can we can find that 3 minus lambda times 6 minus lambda minus 4, this is equal to 0. So this is the characteristic polynomial, second order in lambda. The roots of these, as you suggested, this was lambda 1 was equal to 7, and lambda 2 is equal to 2. Okay, we did this, and then we need to identify the eigenvectors. Okay, to find eigenvectors, we know the following. Let's look at this matrix. And let's remember that we have Ax is equal to lambda x, right? So this is the eigenvalue equation. But, and let me ask you this question. What is the rank of A minus 7i? What is the rank of this matrix?
It will be 1.
Correct. It's going to be 1. Why is this equal to 1? It should be 1 because for this specific eigenvalue, the determinant of this matrix is going to be 0, right? We do remember this, so it's 1. Similarly, the rank of A minus 2I, this is also equal to 1. Fine, we know this. It's one type of theoretical question which could be traditionally be asked in an exam. But let's substitute here 7. We do 3 minus 7. This is, what is 3 minus 7? Minus 4, 2, 2, and what is 6 minus 7? It is minus 1. Now, are these two rows linearly dependent?
Yes.
Yes.
Because if we multiply the second row by minus 2, we do 2 times minus 2 minus 4. Minus 1 times minus 2, 2. So they are linearly dependent, which means that one of them is the second one times a constant. So it is clear that the rank of this matrix is 1. If the rank of this matrix is 1, that means that we can extract only one equation in order to find A and B. And let's not forget that this is equal to 0, 0, right? So now, what is a pair of numbers A and B? And again, let's not forget our classical, what is the basis here? It's 1, 0, 0, 1, right? Then let's start here. What is the single equation that we can obtain from here? We get this 2A minus B is equal to 0, right? And then we have 2A is equal to B. So what is a pair of numbers A and B that satisfy this condition?
1,
1,
2.
That is correct, 1, 2. So this is basis vectors, which is going to be the eigenvector. Then,
minus 2, 1.
which one is minus 2, 1?
The other eigenvector.
Oh, you found it? Okay, that's good, but let's try to find it. Let's double check. So apparently you found it. This is really good. But let's substitute here 3 minus 2. It's 1. Then we have here 2. So we are substituting in this expression. Then we have 2, and we have 6 minus 2. We get 4. So then we ask the same question. What is the rank of this matrix? It's still 1 because these two rows are linearly dependent because the second row is the first one times 2. So this is 0, 0. Then what equation we can get from here? We get A plus 2B. This is 0, and you are right. So minus 2 plus 2 is equal to 0. So this is the standard basis composed of these two vectors. This is the new basis. That is good. So it looks like we could determine what is the matrix P, and matrix P, it is equal to 1, 2, minus 2, 1. So the eigenvectors of this matrix A, the eigenvectors of this matrix, they are put here into the columns of P. Then, what is the diagonal matrix D? 7, 0, 0, 2. So this is the matrix D. And then, what is the P inverse? The P inverse, it's equal to 1 over the determinant, which is 1 over 14. If this is still true, right? It's 14.
No, I think it's 5. 1 over 5.
Yes.
Yes,
It's 1 times 1 minus 2 times 2. It's 1 plus 4.
Wait a second, but this is the determinant.
We need the determinant of P, not the determinant of A.
Oh, yeah, you are right. I was confused. Yeah, we're finding this. What is this? This is 1 plus 4. Yeah, you're right. This is 5. Okay. We bring it back to the. So then we interchange these. We multiply by minus 1. This is 2 minus 2. Okay, that's good. That's the P inverse. And then, yeah, this is all that we need. The next step is the following. Let's find what is U0. So now we have all the tools to solve this one, and let's continue. So what is the next step? The next step, we need to write this. Okay. So how can we write this system? Let's pass on this other side, on the opposite. So we say that the rate of change of U and the rate of change of V, okay, this is equal to 7002 times UV. Okay, so this is what we do. We have here the mixing matrix, and we have non-zero of diagonal terms, which means that y1 it will depend on y2, and y2 it depends on y1. So what we do is that we transform the system into a new basis using these vectors to construct the matrix P in order to conduct the linear transformation from one basis to another. And this is the new equation that we obtain. Okay, so now what have we done so far? We have this system of equations, okay, and now we did all of this work to write this. Okay, now forget what we have, forget this part, and let's solve this system. What do we read from here? We read that du over dt is equal to 7u. So there is no coupling. So let me write here. So there is no coupling between u and v. Okay, they are not coupled, which means that u depends only on u, and v depends only on the v. So this is the first equation. What is the solution of this system? This is u is equal to u0 e to the power 7t. Okay. The other equation, it is that dv over dt. This is equal to 2v. So then we say that v is equal to v0 e to the power 2t.
Profesor,
Yes.
në provim mund ta shkruajmë kështu direkt apo duhet ta shtjellojmë atë me integrale, me ln e gjitha?
You can write it right away. Okay, you don't need to derive it. Okay, so if you see this expression, you can give it right away.
Okay, thank you.
Don't worry. And it is you can consider this one as a trick or as a tool. Okay, yeah. So this is what we have at this part, and what we have not completed is that we have not found the u0 yet, right? Okay, we don't know u0. So what are the initial conditions? They are here. Now we need to know what are these numbers. So we don't know this, right? And we don't know this. So we don't know at time t equal to 0 initially what were these values. And here we can say that u0, v0. How are they related to these values?
P inverse times ui0.
P inverse times x0. So P inverse is 1 over 5. 1, 1, 1, 1, 2 minus 2 times 5 and 5. So this is equal to 1 over 5.
Minus 1, minus 3.
Is it the final answer?
No, the whole is minus 1, minus 3, or 1 over 5, minus 5, minus 15.
You are too fast. For me, this is 5 plus 2, this is 15, right? Is this 15?
Yes.
And this is minus 5. Am I correct? So, minus 10 minus 5. So this is equal to 3 minus 1. Is this good?
Yes.
Okay, then this is going to be equal to 3 e to the power 7t, and this is equal to minus e to the power 2t. Okay, now it looks like we solved the system of equations in the new domain, and it was very easy because we don't have coupling, right? Wait a second, so I think you can see that a little better like this. Okay, so then we found the general expression here. What is the next step? We need to find xt is equal to p times ut. Let's not forget that the ut is a vector and the xt is another vector. And then in this case, you have the following. What is xt? Xt itself, it is this vector is y1, y2. Okay, so we can write this one y1 as a function of time and y2 as a function of time. This is equal to 1 minus 2 to 1. And we multiply this with 3 e to the power 7t minus e to the power 2t. So this is equal to 3 times e to the power 7t plus 2 e to the power 2t. This is 6 e to the power 7t minus e to the power 2t. Okay, so this is the solution as a function of time. Okay, so this is the general solution of this system. One question can be the following: what happens? What is y1 at t equal to 2? Okay, and what is y2 at t equal to 2 again? So this would be equal to, we have 3 times e to the power, what is this?
14.
14 plus 2 times e to the power 4, 6 e to the power 14 minus e to the power 4. Okay, we just have to play with numbers. This is 2.71, so it's like around 3 to the power 14 times 3. This is like 3 to the power 15 plus some numbers which we can substitute using a calculator, and you can find the correct value. Is this clear?
Is it okay if we leave it like that in the exam?
It is perfect to leave it like that, yes. So, yeah. Yeah. I hope this is clear. We have all of the material on the board. We can give a very short break.